steady, non-uniform?
Is overbank flow considered steady, non-uniform?
Yeah, I was just having a little trouble understanding what overbank flow was.
Okay, yeah, we can cover that quickly. So you have your channel, right? I'm going to draw a top view of a small river. You got your little trees, all that stuff, right? So typically the channel is defined as where the fluid, in this case the water, where the water flows consistently, right? And then the banks are that area to the left and to the right of your channel, okay? So overbank flow is when it rains a lot or when you have more flow than the channel can handle, fluid will overflow. But since this is actually sloped, the fluid will continue to flow, just not completely in the channel. Part of the fluid will be on the overbank, and that's why we call it overbank flow. So all the flow that's outside of the channel, but still flowing in the direction of the stream, is what we call overbank flow. It can be steady, uniform, but in real life, it's actually going to be unsteady, non-uniform. Yeah?
Would that be the depth changes? So would that make it uniform?
See, the depth.
Or non-uniform?
See, the depth, when we define the depth, we talk about from the bottom of the channel all the way to the top of the surface.
Because I know that way longer, much longer.
Can you say it again?
Okay, cool.
I'm going to mute you again.
All right, I can't hear. I'm hearing a couple of people, but I need to. Whew. All right.
I think somebody was talking.
Yeah.
That wasn't accurate, but the person muted their mic.
Okay, that's good. Okay, good. All right. So, wait a minute. Did I answer your question about overbank flow before I move on?
I don't think so. I think you were right about to.
All right. So, essentially, when I say depth in open channel, let's say we have a cross section where this is your channel and these are your banks. And the fluid, in this case the water, is flowing both on the channel and on the bank. When I say depth, really I mean the distance from the lowest point in the channel to that surface. So even though when you look at the overbank, your depth is actually smaller, and when you look at the channel, your depth is bigger, that can still count as steady, uniform flow as long as these values don't change with respect to time. Okay?
Okay.
So yeah, we can call it steady, uniform flow, but remember, these are like simplifications. In reality, it's not going to be that, it's not going to be steady and uniform. It's actually going to be unsteady and non-uniform. But for this class, we're going to simplify it as much as we can. Does that make sense?
It does, thank you.
No problem. Who was that? Was that Zach?
Yeah.
Okay, cool. Yeah, don't feel bad if I don't recognize some of your voices. Everything sounds weird on the computer. Okay, so let's see. This is example 12.8. It says the channel in the figure is made of finished concrete. So finished concrete, that should give us a clue that the roughness value is 0.012. In civil engineering practice, we use a roughness value of 0.013, but the book will use 0.012. So keep that in mind if you ever have to work on something outside of this class that has to do with open channel. For concrete, we typically use 0.013. I actually put some values on the lecture notes that I posted. Those are the ones that we use in industry. So if you see any difference between the book and the values that I posted, go with the ones that I posted. Let's see, finished concrete, and the bed drops 2 feet in elevation for a horizontal stretch or reach of 100 foot. Okay, so they're giving us a lot of information. They're saying that, 1,000 feet. They're saying that in 1,000 feet of horizontal distance for this channel profile, the vertical drop is 2 feet. Now this is a profile view, which means that water will flow in this direction. It's not a cross section, it is a profile. Now, why would they give us this information? Because they want us to use it to find the slope. So let's go ahead and find that slope. It says for every 2 feet vertical, we have 1,000.
Hard to the left.
Sorry?
We can't see the all the two. I don't know if it matters or not.
Oh, here you go. Do you see the 2 right now?
Yeah.
Awesome. So it says that for every 2 feet of vertical drop, we move 1,000 feet in the horizontal. So how do we define a slope? If you guys remember from your, I don't know, whatever math classes, a slope is just dy over dx, right? Just y over x. So for every 2 feet in the y, we move 1,000 feet in the x. So we plug this into a calculator. That should be about 0.002. Does that make sense?
Yes.
Okay. So we got 2 feet. So this is feet on the numerator. 1,000 feet on the denominator. The feet cancel out. So that should give you a clue that the longitudinal slope is dimensionless. Okay? So keep that in mind, because there will be other problems where they give you the slope as a percentage, and you have to convert it from a percentage to a dimensionless decimal in order to apply it into the Manning's equation. Okay, so they give us the slope information. It says, determine the steady uniform flow when the depth of water is 4 feet. Okay, and then they give us a little picture of the cross section. They actually give us an orthogonal view, but we don't need it because we already have the slope. So if we look at the cross section of this channel, we have a 6-foot base and a 4-foot depth. So 6 feet base, 4 feet depth. Okay. So how do we solve this problem? Any ideas, recommendations, suggestions?
Go ahead and start with the R value, with the area over wetted perimeter, the hydraulic radius.
Okay, so let's do that then. Who was that? Was that Michael?
Zach.
Zach again? Nice.
Yeah.
All right, cool. So you said you wanted to start with the hydraulic radius, which requires the area and the wetted perimeter. So let's go ahead and do that. For this channel flow in a rectangular channel, what is the area, Zach?
That would just be 4 times 6.
Yep. So 24, right?
Yeah.
24 squared feet. Good. Somebody other than Zach, for this rectangular channel, what would the wetted perimeter be?
14.
Yep. So 6 plus 4 plus 4, so that's 14 feet. Thank you, whoever said that. And now, someone else. How do we find the hydraulic radius?
Just plug your computer in.
Yes.
A over P.
Thank you. A over P. It's kind of weird, again, not being able to see your faces and knowing who's talking. But yeah, A over P. So the area is 24 square feet. The wetted perimeter is 14 feet. 24 divided by 14 is
1.714.
1.714. Foot squared over foot cancels out, so we end up with 1.714 feet. Good. So we did it. Thank you, anyone who participated. Now, new persons. What next?
Plug and chug.
Plug and chug. I like it. I like it. Okay, but plug where?
Into the menu. Into the flow rate.
Exactly, into the Manning equation. Good. So our Manning equation for flow rate is flow rate equals K over N times the area times the hydraulic radius to the power of 2/3 times the square root of the longitudinal slope. Let me check if this is still recording. Oh yeah, it is recording. Good. All right, plug and chug. Do we know flow rate?
No.
Do we know K?
No.
No.
Yes.
Yes.
I think we do know K.
Yeah, we,
K is a conversion factor, right? So what is K for this problem?
1.486.
Exactly, right? This is an English or US units problem, so K is just 1.486. So we do know K. So 1.486. Do we know N?
Yep. Point 0.012.
Do we know area?
Yes.
Do we know the hydraulic radius?
Yeah.
Do we know slope? Yeah. All right. Without looking at the book, plug it into your calculators and give me your answers. Let's see if we can actually get the answer right without having to look at the book for the answer.
$190.36.
All right. So somebody got 190.36 cubic feet per second, right?
Yeah.
Awesome. Can somebody confirm that value?
Yeah, that's right.
Good. So we learned how to use Manning's equation. Congratulations.